Okay, and we are on. Good afternoon, everybody. Hope you've had a chance to caffeinate after lunch so we can avoid the dreaded lunch coma. Hopefully I'll be engaging enough to keep you awake as well. So let's jump into it. So I'm Dave Salvatore, Senior Director of Accelerated Computing Products at NVIDIA, and work closely with the Azure team here to bring NVIDIA technology into the Azure environment. So what I'm going to be talking about today is a lot of the ways that we work together with Azure, as well as taking you through sort of, I'll call it a guided tour of our entire platform. And that's a really important word when you think of NVIDIA. There's a tendency to think of NVIDIA as, oh yeah, those GPU guys. We are in fact a data center platform company. And as I move through the material, you'll sort of see what I mean by that. So generative AI has obviously been the thing that has been the white-hot focus area in AI research, and with a particular focus on LLMs, large language models. And generative AI can, as you guys are probably aware, can solve for an amazing number of problems. I'm not going to read the whole slide to you, but this gives you a sense of, oops, let's see, go back, there we go, of just what's possible with generative AI. And in a lot of ways, it's still very much the early innings of AI, of Gen AI, I should say, in particular, in terms of use cases. And I'll talk a bit more about that, again, as we move through the talk. The interesting thing now is generative AI, and I say that because the first about 10 years or so of AI was really more about detection and recognition, right? Whether that was images, language, audio to some degree as well. And then we sort of began getting into natural language processing and understanding, particularly with the advent of a model called BERT, which was first described by Google in 2018. This was the first model using a new model architecture called the transformer architecture, which some of you may be familiar with. This architecture has been absolutely a game changer and has really been at the heart of a lot of the current leading edge large language models that we're all using today, particularly the large community models that some of you may be developing on. What's different with generative AI is, like the word suggests, it's AI's ability to now generate content, right? Whether that's generating synthetic data, computer code, text summaries, translations, a whole host of things. Also generating images, generating even videos now in the not too distant future, generating rendered 3D, and even generating potentially even gaming worlds, right? So again, very early innings on generative AI. So the promise of what it can do for us in terms of the things it can create, the things it can help us create, the ways it can accelerate innovation we're very much in the early days of that. So what does it take to actually deliver generative AI? Well, the first thing I'm going to say is platform. So there's that word again, right? What do I mean by platform? What I mean is that we, NVIDIA, make pretty much everything you see on this slide, right? With a special focus in the upper left-hand corner of the slide, you see all the software we work on, right? We do a huge amount of software work at NVIDIA. So much so, in fact, we have twice as many software engineers as hardware engineers, which surprises a lot of people because, again, of the what I'll call historical association with our hardware. But with particularly the Blackwell design, and that's kind of what you're seeing there in the middle of the slide, is a Blackwell, what's called a GB200 NVL72 rack that also includes the liquid cooling unit, which we call a sidecar. What you're seeing is just a whole variety of hardware that we make that comprises the platform. This includes, of course, our GPUs, also our CPUs based on the ARM instruction set architecture, our NVLink switch chip, and again, I'll talk a bit more about each of these components as we move through the talk, and then our networking accelerators, both for top-of-rack switches as well as for our smart NICs. So all these things have to come together and work well together in order to make Gen AI possible, right? Generative AI absolutely requires acceleration, right? There was sort of this conventional wisdom in some of the early years of deep learning, in the first decade or, ish, that you could do your training on GPUs and then deploy on CPUs because, hey, we've got lots of CPUs. They're sitting around. They're not doing much. Let's put them to work doing inference. And that worked for a little while, but generative AI has definitely raised the ante, right? And what I mean by that is that the compute required, not only for training, but also for inference, has increased dramatically. And I'll cover this a bit more in a minute. So much so that if you think about Gen AI applications, particularly those running based on good-sized LLMs, this is like, think 70 billion parameters and above, there's an expectation not only for high-quality answers, but high-quality answers delivered in real time. And when you compound those two things together, that drives the need for not only multi-GPU inference, but even going forward, multi-node, multi-GPU inference. And that's one of the things Blackwell was born to do. And I'll I'll touch on that a bit more in just a moment. So in terms of what's available on the Azure platform today, right, I'm just showing here sort of the selection of instances of some of our current generation products. The most recent arrival was the H200 v5, which is now generally available on Azure. That's based on our Hopper architecture. Also based on the Hopper architecture are the next two you see, which are the H100 and then the H100 NVL, which is basically two H100s that are paired together and connect to each other over our NVLink fabric. Right? The first two selections you see there, which are 8 GPUs per VM, we're getting a little ring here in the audio, guys, a little bit of feedback, use our NVLink fabric technology and our NVLink switch technology. These are both critically important. Okay, let me take a step back. I think we're getting some feedback. And the NVLink switch chip is critically important to accelerating this platform because not only do the GPUs have a ton of work to do, the GPUs have to talk to each other all the time to do that work, especially for training. And increasingly over time, for Gen AI inference, as we move into different types of parallelism techniques, inter-GPU communication becomes another critical performance factor that has to be managed and optimized for. And then lastly, we have, based on our A10 GPUs, the NV80 A10 v5. This is a particularly good solution for visual computing, as well as it can be used for what I'll call mainstream AI inference as well. And that is based on our Ampere architecture. Right? So I'm going to kind of walk you through some of the components in the system. And the next one is going to be our InfiniBand platform. And I mention this because, particularly here on the Azure platform, it's a very important platform, or platform component, I should say, that really keeps things moving. And Azure has done a number of submissions to MLPerf, which is an industry standard benchmark. There's two components. There's a training component and an inference component. In the training component, they've done very large-scale submissions and really shown phenomenal performance and scaling efficiency, some of it due in good part to the presence of InfiniBand networking. Azure went in early on InfiniBand with us and has stayed on the InfiniBand networking platform as kind of their networking platform of choice, and it shows up in their results. You know, they have very strong, not only sort of per node performance, but also strong at-scale performance as you go to use tens, hundreds, or even thousands of nodes, right? And to wit, you know, one of the things that's happening concurrently with this conference is, of course, supercomputing 2024. It's happening down in Atlanta. And the top 500 list, which some of you may be familiar with, sort of ranks the most performant supercomputers in the world. And on the latest list, we're kind of proud to say that there's a #1 entry there called Eagle, which is the #1 public cloud entry in the top 500. So when you think about very high performance, not only for AI, but also for scientific computing, scientific simulation, Microsoft and Azure are, of course, offering you know, very compelling solutions, again, sort of on the per node basis as well as at scale. Another important component to the platform, we started this in the Hopper platform. We will continue it as we move into the Blackwell platform, is confidential computing. This creates a trusted execution environment between the GPU and its memory, where all data that moves between those things is now encrypted, and it's part of a trusted execution environment. You know, sort of the diagram on the left side of the slide sort of helps you kind of understand somewhat, you know, where how the confidential VM sort of extends its sort of trusted execution environment down to the platform level. And so there are currently H100-based offerings. It's called H100 v5 confidential VMs is the long product name for that, or the long instance name for that. And the work is ongoing with Azure to continue to bring confidential computing to more GPU instances. Can't get into particulars at this time, but you can sort of forwardcast as to what some of the other places where that might show up. As a quick by the way, as it relates to confidential computing, we've added some additional features in the Blackwell architecture, most notably a dedicated encrypt-decrypt engine, sort of its actual fixed function logic unit in the Blackwell architecture, whose only job in life is to encrypt and decrypt content in the trusted execution environment. Historically, sometimes with encryption, there is a bit of overhead in terms of the encrypt-decrypt as you're moving data around. And so one of the goals here with the Blackwell architecture and this dedicated engine is to remove as much of that overhead as we can, the result of which is an ability to run encrypted with basically near zero performance hit. And that's an obvious sort of goal as to why we'd want to do that. You kind of want your cake and eat it too. You want the best performance, but you also want to be able to operate securely. And this has relevance to a wide variety of industries, right? Particularly heavily regulated industries where there's a lot of data sensitivity. Healthcare, financial services are two great examples. And then also for governments that are thinking about sovereign AI around the world, as they go to think about their AI strategy, which many view as part of actually a strategy as part of their broader national security, the ability to work with sensitive data that is confidential becomes important. So that ability to run it encrypted, to use confidential computing, takes on additional importance for them. So it's something that a lot of governments around the world who are formulating their AI strategies, again, this kind of being called now sovereign AI, are very interested in encryption for fairly obvious reasons. So let's talk for a few minutes now about performance. So our H200 Tensor Core GPUs, which is the latest version we have on our Hopper architecture, we basically upped the ante in terms of both memory and memory bandwidth. And then we also were able to bring more performance both for AI as well as for high performance computing, right? And you see some of the X factors there down below, right? Up almost 2x more performance on inference, as well as a huge performance gain on Milk, which is an HPC simulation, and I believe that's versus CPU, right? So the point being is that the Hopper architecture, which has been in market for some time now, continues to deliver great performance, right? In fact, in any given architectural generation that we put into market during the product life cycle of that architecture, we will typically get about another 2 to 2.5x more performance from software optimization that we're constantly doing. We actually release new software on a monthly cadence. It's available as containerized software that supports models, frameworks, a whole variety of things, much of which is available both from GitHub and NGC, right? And then there's some additional ways we make it available that I'll talk about here in just a few minutes. So I talked earlier about NVSwitch, right? And it's important. So NVSwitch basically is our dedicated switching technology that lives on the baseboard along with the GPUs. And what it allows for is all-to-all communication between all the GPUs, all 8 GPUs in that system, over the NVLink fabric, which is about 7 times faster than PCIe and much, much faster than any networking technology. This is especially important for training, as inter-GPU communication to do things like all reduce and all gather operations is a critical part of that operation. And once samples are run through, if there are error terms that have to be back propagated, that all has to be communicated to all GPUs. Some of this will depend on the parallelism techniques being used, but that aspect of inter-GPU communication is critical to good training performance, whether that's pre-training, where you're kind of starting from zero, or even doing fine-tuning, where you're taking a pre-trained model and applying your own data set to it to essentially give it knowledge of your sort of informational domain, right? So, the most recent round of MLPerf training, which these results just dropped on November 13th, we were able to actually get 30% more performance, even versus what we submitted about 6 months ago. We're very pleased with that result. And again, that's just further evidence of the ongoing work we do to make our software better. The optimizations that go into MLPerf are the same optimizations that go into our containers that we make available to the community. And again, these are available from a variety of places. I mentioned GitHub and NGC is two good places to get it. And there's additional ways to get those containers with some additional features that I'm going to talk about here in just a minute or two. So again, this just kind of is a double click to just sort of show you that pretty much across the board, with H200, we were able to continue to grow performance, right? And so this is important because we're doing this also, by the way, in the same power envelope. That's worth mentioning. These are both 700 watt parts, right? So and here again, we're getting up to 27% more performance, between comparing the two GPUs, right? So we're very pleased with that progress. And of course, Blackwell is going to take us kind of to that next big stair step performance gain, which I'll talk about also in a few moments. So speaking of that, one of the things that continues to drive us, to drive our innovation, is the fact that no matter how performant we build our systems, developers always want more, right? Which we're very pleased about, because what it means is that there's still a lot of innovation, a lot of learning, and a lot of new applications that can be brought to light, brought to market, to help businesses, realize more insight, more value from the huge amounts of data they've gathered through the years, and then also put that data to work in newer applications to help streamline business, whether that's to reduce costs, increase revenue, or some combination thereof. But one of the things it's also driving has been just the explosive growth in model size, right? We're showing here, some of the models that have been out there, including, one very, very large model, which is GPT, MOE, that's Mixture of Experts, which is a 1.8 trillion parameter model. This is an absolutely massive model. And it's that drive, and you can see there, I talked about the transformer architecture a few minutes ago. You can just see sort of the slope of that growth line, over the last couple of years. And it has been just a rocket sled, right? The rate at which the models are growing in size and also complexity. In some cases, there are some developers who are working with LLMs of a somewhat smaller size on the order of 7 to 10 billion parameters. But what they do is they run many more samples through that model. They use a much larger data training set, or training data set, yes, that's right. And it's a way to make the model smarter, get higher quality answers, and then be able to save money once you go to deploy because the model is smaller, right? You can use less infrastructure to serve that model. So there's a lot of different experimentation going on. Innovation and experimentation sort of go hand in hand because innovation means doing something new, something you've never done before. And that often involves a lot of iterating, a lot of, frankly, failing fast, learning, and trying something else. And that's another thing, frankly, our performance enables, is it allows those researchers, those developers to try things and see if they work and get a result faster and then understand if it doesn't, okay, let's course correct and try something else, right? So that's another role that the performance plays in bringing these innovations to market. So I've touched on this, but it's important to understand, and in some ways I kind of stole my own thunder here, that Blackwell is a platform, right? It starts with the GPU, but that's the key sentence. The GPU is just the beginning, right? All these other components go into making the Blackwell platform happen, in addition to the software stack that I showed you in the earlier slide, right? So this includes, of course, the GPU, our Grace CPU, right, which I talked about, the NVSwitch for our NVLink fabric, as well as our networking accelerators, both for our SmartNICs and our top-of-rack switches. Down below, you see the different blades that go into the Blackwell racked system. This includes a compute blade, as well as an NVLink and NVSwitch tray, and then one tray either for Spectrum or quantum networking. We offer both Ethernet and quantum and InfiniBand networking, depending on which a shop wants to use. We think they're both good technologies for networking. That said, our Spectrum technology, the technology we have in our Spectrum Ethernet top-of-rack switches in particular, is really more purpose-built for AI in ways that, frankly, traditional Ethernet wasn't. And I'll probably talk a little bit more about that in just a moment. So now just kind of double-clicking on a few of the component pieces. The Blackwell GPU itself, again, it was sort of born to work on these massively, just basically massive LLM-type models and generative AI models. And so, with that, we've built in a ton more compute. We've added the FP4 precision support, up to 20 petaflops of AI performance in a single GPU, which for those of you who know your petas from your exas, from your teras, know that that's just kind of a mind-blowing number, right? We've also added support, again, as I mentioned, for FP4 precision. We actually used FP4 precision for our very first submission to MLPerf inference on the Llama 270B language model. And not only did we see that 4x performance bump I talked about, but we're also able to preserve accuracy such that we passed all the accuracy tests that are in the benchmark. You can't just go faster in that benchmark. You have to pass quality tests as well. And our FP4 implementation not only delivered that speed up, but also passed all those quality tests, meaning we could make what's called a closed category submission, which is sort of an official submission, right? And so we were very pleased with that outcome, and that's work that we continue to do kind of at the software level, because that's where you have to get into very intelligent quantization algorithms to be able to bring FP4 into an implementation while preserving accuracy, because a lower precision does you no good if it's going to tank your accuracy, right? And quantization, by its very nature, will introduce basically rounding errors, right, into answers that can ultimately lead to a reduction in the quality or the accuracy of those answers. So this is work that we will be continuing to do and continuing to learn about in the Blackwell cycle. And we'll bring those learnings into our software, things like TensorRT LLM, ModelOpt inside of TensorRT, and other libraries to help enable developers to use FP4 and get benefit from it, both in terms of performance as well as preservation of accuracy. So next up is NVLink, and again, I've talked about this a bit. I won't dwell on this too much. This is our 5th generation of NVLink, and it brings with it some fairly interesting stuff, including version 4 of what's called our SHARP technology, which basically is for in-network compute. So not only do we have, of course, massive amounts of compute in the Blackwell GPUs, but we also now have a certain amount, basically 3.6 teraflops, it says right there, of in-network compute that can be done on the NVLink switch chips. So this is a way to help offload certain operations. We also have some of this in our top-of-rack switches as well as a way to help, again, offload certain types of compute, as well as to help calm network traffic somewhat by not having to necessarily push as much stuff across the network, right? So, so again, this is a critical technology that enables us to run in our multi-GPU and also in going forward multi-node configurations, as Blackwell will bring together 72 GPUs across multiple server nodes, all communicating over NVLink fabric using NVLink switch. And then, of course, this is kind of the beast. This is a GB200 NVL72 based on our Grace Blackwell. And again, this is basically going to be 72 of our GPUs all talking to each other, and then 36 of our Grace CPUs all talking to each other. And you see some of the flops numbers down there. And again, pretty astounding numbers. Basically, in a single rack, you're looking at more than an exaflop, basically 1.4 exaflops. We've had a number of partners announce very large supercomputer systems, some of which will even go into zettascale. And so, you know, Blackwell's going to enable some amazing, very large-scale systems that are going to be able to work on just very knotty, huge problems, both for AI as well as scientific simulation, in ways that were just previously not possible. And again, I've talked a bit about, you know, the explosive growth of models, but, you know, another way to look at that and think about it, if you look on the left-hand side of that slide, in terms of how many GPUs you actually need to get work done across these different models, and again, we're sort of doing this somewhat over time, what you can see is that all told, you know, as we get more performance and as we learn more from the software optimizations we are continually doing, we're able to do the same work with fewer GPUs, right? Less infrastructure, less deployment cost, right? And so these are all key factors for developers, for business organizations, for DevOps and infrastructure managers who are thinking about, you know, how to basically how to allocate these resources and how to provision these resources to different teams. By having additional performance, it lets more teams do more things and also lets the teams doing their work hopefully get that work done sooner so that that resource can then be passed to another team or another team to do their work, right? And so, you know, if we think about as well then thinking about scaling over time, and again, we sort of have this on the right-hand chart where we're looking at the different compute fabrics. And what we're seeing here is that, you know, as we think about, you know, what I call a sort of standard fabric versus using Quantum X800, which is our InfiniBand networking, we believe over time that we're able to deliver significantly more performance using InfiniBand for those customers who want InfiniBand. As I mentioned, we offer both InfiniBand and Ethernet. And so, you know, this is why we, again, I'm sort of reiterating what I talked about before, but this is why we built Blackwell, right? Blackwell was built to solve these really big, challenging problems. You know, we were able to bring in just massive amounts of compute, massive amounts of performance and interconnectivity at not only the GPU or even the server level, but even at the rack level and even out to the data center level. When we think about system design at NVIDIA, we are thinking at the data center level. We sort of think of the data center as the new unit of compute. You may have heard that in some of Jensen's talks. And that's very much how we think about system design, frankly, because we have to, because that's what AI demands. AI demands scale, right? And so in order to be able to build at scale and enable partners like Azure, we also, from day one, we're thinking about how are we going to scale this out? How are we going to scale this to tens, maybe even hundreds of thousands of GPUs and then, you know, an attendant number of CPUs over time, because that's what we believe the market is telling us it wants. So in terms of Blackwell and its performance, we've done 2 submissions this year. We did a training submission, which was the most recent one. We were actually able to, on a per GPU basis, set new records on all 7 of the workloads in the benchmark using Blackwell. And the performance speedups we were seeing was up to 2.2x. We have the 2 LLM workloads called out there in particular. And we're very pleased with this result. This is sort of an early days submission, right? As I mentioned, you know, software optimization is sort of ongoing. We expect some of these numbers to grow, and as the workloads grow in size, MLPerf is constantly, the consortium that builds MLPerf is constantly looking at new workloads. And that has to do with basically the rate at which AI is evolving. And MLPerf, is typically revving the workloads in that benchmark once or twice a year in order to sort of stay apace with the industry. And generally speaking, we think they're doing a pretty good job. So, but as the workloads grow, for instance, there's a version of Llama 3.2 that has 405 billion parameters, right? As you grow the size of the networks, the performance advantage of Blackwell, it will just continue to pull away, right? Because again, it just has so much more headroom than its previous generation. And then I touched on this one a few minutes ago, our MLPerf inference submission. This is the one we did using the FP4 precision, wherein we were able to meet all the accuracy targets and make it an official submission. Very pleased with this as a first result submission for MLPerf inference. This is a video that I wanted to just show you guys. It's about a 1 minute long video that where Microsoft is talking about the Blackwell systems that they're building in their data centers, which were actually announced by Satya in his keynote yesterday as being available in private preview for a select number of customers. As we move into the new year, there'll be more news coming from Azure about when they'll make available their Blackwell instances for their larger customer base. So let's just have a quick look at this video, and then we'll be right back. Can we get audio for that, please?
Change the face of industry. Microsoft and NVIDIA are forging a new path of innovation and redefining what AI can do for everyone. Microsoft brings the new NVIDIA Blackwell platform to the cloud, combining the NVIDIA GB200 NVL rack design and NVIDIA Quantum InfiniBand networking to power purpose-built Azure instances that deliver groundbreaking performance for AI workloads. Microsoft infuses innovation at every layer, from our advanced liquid cooling Sidekick to technology that boosts and optimizes server processes to security at the hardware level, all enabling optimal performance for the Blackwell platform on Azure to accelerate state-of-the-art generative AI. From turning simple prompts into complex software to transforming intractable questions into historic breakthroughs, generative AI has taken its place at the forefront of human discovery. Together, Microsoft and NVIDIA are powering the AI innovation that empowers greater human invention.
Okay, so that gives you just sort of a sense of what it takes to build infrastructure of this scale. It's not a trivial thing. And then this is just a little bit of more details about the instances that will be forthcoming. The name, of course, the ND GB200 V6 will be the name again. It's up to 72 of our Blackwell GPUs, all talking to each other via NVLink switch. Again, InfiniBand networking, and then the rack scale design was actually something that we've developed a number of sort of reference rack scale designs, and as a way to help get to market faster, Azure is using that rack scale design in their build out of Blackwell. So the partnership with Azure that we have, you might think of it as being, because I've talked a lot about hardware, certainly. We also, of course, have services of our own that are available through the Azure Marketplace, and I list some of those here. There's DGX Cloud, Omniverse Cloud, NVIDIA AI Enterprise, and NVIDIA NIM, and I'm going to talk a little bit about each of those. But even beyond that, there's so much more to the collaborative work we do together with Azure, and it extends into many of the services that Azure offers, which are actually being accelerated by NVIDIA technology. It also involves integrating a lot of our software stack into the Azure environment to facilitate the use of NVIDIA technology on the Azure platform. And this is something that we're doing on an ongoing rolling basis. We're doing a lot of work with Copilot, of course. We're doing work with the OpenAI service that's now available from Azure, and a number of other things, including the Azure Container Apps, which was announced here at the conference, actually. And then in terms of just customers and people who are on the platform using NVIDIA technology, this is just a small sampling of those in terms of enterprises and ISVs. And then, of course, you have GSIs, which are global system integrators, and solution development providers, SDPs, as well, who can help enterprises figure out how to build their applications and deploy them on Azure. And then, of course, also we have our Inception program where we're working with over 1,000 startups, many of whom are then bringing their technologies onto the Azure platform to develop and to deploy. So if you think about The other key piece of our platform is it's not only full stack, but it's also end-to-end, right? This is also really important as a way to speed development, because it lets you essentially stay in one development environment, as opposed to having to say, do a certain amount of work over here, then try and bring it into this other environment, hope everything's compatible and will hopefully just work. And then from there you go to deploy, and that might even be a third thing. What we allow you to do, and again, this is both in sort of our NVIDIA's own technologies as well as technologies we've integrated into the Azure platform, we allow you to do that development end-to-end, from the acquisition of the data to the final deployment of that data, using either our Triton Inference Serving software or using other Azure tools to develop and maintain that application, right? And so that end-to-end aspect is super important, because there are quite a few steps involved in finally getting an application ready to deploy and make sure that once it's deployed, it's going to run well and that you're going to have good uptime as close to 24/7 as possible. So one of the technologies we make available, it's a technology and a service, is called NVIDIA AI Enterprise, also available through the Azure Marketplace. This is a combination of our optimized and security scanned containers that we release new versions of on a monthly cadence, as well as enterprise class support directly from NVIDIA, particularly for those organizations who are maybe just getting started with deep learning or are wanting to have NVIDIA expertise as they build out their application. NVIDIA Enterprise is there to help, right? And so this is an interesting program, again, available through the Azure Marketplace. And I would encourage you to check that out if you're an organization who's wanting to start to really build using generative AI and wants to get basically some help and some coaching from NVIDIA, in addition to the help you'd be getting, of course, from Azure. Let's see. Jump to. Another resource we make available is called NIM. This is NVIDIA Inference Microservices, right? This is where we basically take across a number of different categories, trained networks, and then we containerize them with all the necessary sort of supporting acceleration software, things like TensorRT LLM, for instance, and put that all into a container that can be very quickly deployed on the Azure platform, right? The goal of these is to be able to deploy a model in a matter of sometimes even minutes, as opposed to days, weeks, months, right? The goal here is to get to market faster. The sooner you can get something deployed and up and running, the closer you're going to be to seeing return on your investment. And for a lot of folks who are very focused on the business aspect of deploying these technologies, time to market and how fast, time to return on investment are very important metrics, right? And then, just as a quick performance note here, this is just showing, without NIM, the performance you'd see at a baseline versus with NIM, we can more than double the performance, right? And so this is just an example of, and I talked earlier about how performance drives return on investment. Basically, performance is a form of essentially, I'll call it free value, which is to say, as we improve our performance, as we bring more acceleration, that brings more performance to developers who can in turn then either build more elaborate applications or run their existing applications with less infrastructure. With NIMs, there's a number of ways to deploy them on the Azure platform. You can either just deploy it directly on one of the N-series VMs. You can also deploy it on the Azure Kubernetes service. Many of our technologies are tightly integrated with Kubernetes, most notably our Triton Inference Serving software. And this allows for things like orchestration as well as auto-scaling, which are important features to help maintain the application once it's deployed, and also be able to spin up and spin down compute resources on an as-needed basis. Or, the third option is deploy via either Azure AI Studio or Azure ML, right, which are other development environments that Azure makes available. So the point being is that we didn't just deploy NIM one way and one way only, right? We deployed it in such a way that you have choices about how you want to deploy it. So while we're making it easier by containerizing everything, we also give the option of essentially 3 different paths to take it to market on the Azure platform. We're also taking NIM sort of a step further with what we're calling NVIDIA Blueprints. These are very use case specific containers that we're building out and making available. And again, I won't necessarily try and read all these to you, but just a couple of examples would be things like Digital Human for customer service as an interesting one. Vulnerability analysis for container security is another really interesting one, which kind of maps back to the discussion about security. Virtual assistants for customer service is another great one. And then things like visual agents is another very interesting area. And again, this is basically the first couple that we've put out there. More to come, right? Many more to come. This is the first half dozen or so we're making available. We'll be making many more available as we move into the new year. On a related note, this was an actual announcement here at the show around Azure Container Apps. This is serverless GPUs by NVIDIA. This was announced here at the show to be made available very, very soon. You can see a demo of this at our booth number 400, if you want to swing by, have a look at that and get your questions answered. So I would encourage you to do that. I believe the QR code will also take you to an informational page if you want to get a snap of that. Let me press ahead here. I got about 10 minutes. So another interesting way that NVIDIA technology is being applied is the digitalization of a lot of different business operations, right? Whether that's looking at things like performance, the construction of things like warehouses and factories using what's called a digital twin. The digital twin concept, we've even extended it to things like atmospheric modeling, right? And so this is something that we continue to do a lot of investing in. And it's one of those things that really brings together two of our really main areas that we've done so much work in, sort of our heritage, which is visual computing, right, 3D graphics, as well as AI and simulation, right? And they all come together in a platform we call Omniverse. And so there are a lot of different ways that Omniverse can be used. Robotics is another really interesting one as we continue to move down the path with robotics of being able to basically build robots in a virtual space, have them learn, teach them, and then once they're ready to deploy in the physical world, they will already have a lot of the training they need to be effective from day one, right? So the Omniverse platform, again, as I mentioned, brings together visual computing, what's called physics-informed neural networks, so that the virtual environments you create, these can be collaborative environments where multiple people can be working on projects together, will obey the laws of physics in this place we like to call the real world. And you can then basically build on these things, iterate together. Digital twinning is a really interesting aspect of this as an example where you can build a virtual factory or virtual warehouse and basically move things around inside that warehouse and then sort of test those configurations. What's the optimal configuration for, say, a warehouse? And that includes not only sort of where you're going to put which shelf or where you're going to store what, but it's a matter of pathways. Where are for instance, your roboticized forklifts or things that move pallets? What are the paths they're going to take? What are the paths for your workers? How do you make sure that those things are well spaced and well laid out for not only efficiency, but for safety? Things like this. And this can all be done in a virtual environment before ground is ever broken on that factory, right? So it's a way to build the most optimized factory because once the factory is up and built and you start putting all the heavy things that typically go into a factory or a warehouse, moving them around gets very hard and very expensive. Not to mention you have to take the warehouse offline to do it, right? So a lot of interesting applications that Omniverse makes possible. It also uses a format I'll just mention quickly called OpenUSD. This is Universal Scene Descriptor. This is a format that was originally created by Pixar, and it's a format that we've adopted in Omniverse. This is basically a format to describe 3D objects, right? And what it allows you to do is be able to move those objects around from different environments and know that the object that worked in this environment, this design space, will work in this design space because both are using the same, basically think of it as a file format of OpenUSD, right? So that's one of the key kind of enablers here that makes this a really interesting technology, again, for visualization, simulation, and then things like digital twinning. So here's an example of just kind of a workflow to give you an idea, what this can look like. This is actually a real-time IoT data for digital twins, and again, using 3D remote modeling. So you can see the remote operator on the far right-hand side. And you can see there's quite a few steps, but I think the other thing to take away from this is the level of integration, right? Look at all the pieces of this that are being used that combine both NVIDIA technology as well as Azure technologies, right? Including things like Power BI for data visualization as an example. And then going through and looking at all these different pieces. And these are the kinds of things that we're building as sort of ready-made environments, right? To again get people up and running more quickly. But it just gives you a sense of the amount of integration it requires to build a platform like this. And again, I think this really speaks to the level of collaborative work that we do with Azure to not only bring great infrastructure, but also bring great software and development environments to let developers more easily build applications that can be deployed faster. And so I'm going to pivot a little bit here. One of the interesting things we've been hearing about a little bit is what's called AI PCs. And PCs can be sort of thought of as an edge device, right? And so different AI workloads, need different amounts of compute, right? For light workloads, things like NPUs can be a viable option. But for heavier workloads, you're going to need acceleration, right? That can even be now a desktop or even a laptop GPU, right? Some of you, as an example, one simple example might be, you might have heard of this thing called Ollama, which allows you to run certain LLMs locally on your own computer, particularly if you have a GPU. And so, there's some interesting things that can be done at kind of the client PC level. And there's a lot of interest from Microsoft in this. You heard Satya talk about it yesterday. And then lastly, from a workload category is, the cloud scale workloads that really require data center. These are the things that are just completely impractical to try and run locally on a client PC or even several client PCs networked together. So to that end, we have what we're calling the RTX AI PC. So RTX is our technology for ray tracing. It is an absolutely central feature to our latest generation of GeForce GPUs, and it enables beautiful lighting effects and other types of effects in games that takes lighting to a whole nother level, right? But that same technology and the GPU technology in general, not only is it great for 3D graphics, it's also great for AI, even at the client level, right? So as you look here, at the amount of sort of compute that becomes available, in that second square there, you can see that the relative performance of the GPU and its ability to do AI, even locally on a PC, is dramatically more than what you could do ever with a CPU. And again, as we move forward with AI, those requirements don't go down, right? They only go up, right? So as we continue to bring out new generations, not only of our data center GPUs, but also our consumer GPUs, our GeForce branded GPUs, you're going to see some pretty interesting applications start to land on Windows PCs that can be accelerated by our GPUs, right? And so this just kind of goes towards it as well. I mean, as an example, here's the Llama 3 8B, 8 billion parameter model. And this just gives you a sense of the additional amount of performance that our GPUs make available, on the order of about 14x more performance than you could with the CPU. And and that takes several forms, right? That takes the form of higher throughput, but it also takes the form of lower latency. So as an example, if you happen to be running some kind of a chatbot agent locally on your PC, you want to get the answers back quickly, and you want to have good answers. Having that additional performance enables both things. The other thing it also enables is faster what's called token-to-token latency, which is not only how quickly did you start getting your answer, but how quickly did that answer flow in once it started coming to you. Because we don't necessarily read linearly. We may want to jump ahead. We may want to scan. We may read first sentence of each paragraph to just sort of get the gist of what's being told to us. And so having that come in more quickly will make ultimately for a better user experience. So this is my last slide, and I've got about 2 minutes. I was hoping to have 5, but I guess I talked too much. In terms of some call to action, please stop by our booth. Come see what we have going on at the booth. We have some very interesting demos. Would encourage you to come by and check that out. Do experiment with NVIDIA NIM. Check out ai.nvidia.com, as well as our launchpad for basically starting to run things like proof of concept type projects that you may be considering. And then, of course, look into NIM and NVIDIA AI Enterprise. These can also be experienced on ai.nvidia.com as well as build.nvidia.com. I would encourage you to check those out as well. And then this is my last slide. So again, basically repeating what I just said, please visit the booth and do check out developer.nvidia.com and learn more about building things on our platform in the Azure environment. And with that, I've got about a minute or so. If there are any questions, there's a microphone right here. Feel free. Yeah, go ahead.
Can you hear me? Yeah, I have a question about the Blackwell, and then can you comment about how to design around to improve the heat, to reduce the heat and the cooling? There's a lot of buzz about overheating. Could you comment on that?
Yeah, we saw that article. Look, we continue to work with all of our partners. The chips are running within expectation. We are continuing to do power on and basically bring up of these systems with our CSP partners, including Azure. So far, they're basically running to expectation. So the article frankly had some inaccuracies in it. I can't get into all the details of it. But what I can tell you is that the parts are running within spec, and so far the bring up work is going well. Any other questions? Okay, well, I'll be off to the side here for a few minutes if you have any other follow-up questions. I thank you for attending and enjoy the rest of the conference.